Hi, welcome to Workshop 11 on Hierarchical Data Structures. Today's lecture will continue from where we stopped in the previous lecture. We have a lot of things to cover during this workshop. We will look at the basic properties of a B tree, and we'll also look at the basic properties of a B plus tree. Once we are done with the properties, we will now introduce the algorithms to handle B tree and B plus trees. Under this, we will talk about how we can search for an item in a B tree or a B plus tree. We'll also talk about how we can insert or delete an item in these two trees. Apart from that, we'll go further to talk about why B tree are used for external storage retrieval, especially in a database. So the first part of this lecture will introduce a definition of a B tree. We'll also talk about the basic properties of a B tree and give a comparison between a binary search tree and a 2-3 trees. We'll implement some basic algorithms to handle a B tree in the first part of this workshop. We'll also talk about how and why B trees are used for external storage retrieval.
One thing we have to note about B tree is that it is a self-balancing multi-way search tree. And it has this term called order. That order refers to number of data items a node can contain. And with the value, we can determine the number of data items that can be between the internal nodes. So for instance, if we have a number of data items that is 5, that means that each node within, apart from the root node, will not contain more than 4 data items. And another thing about the B tree is that all the leaf nodes must be on the same level, which is similar to the 2-3 tree that we have discussed earlier. Then to use the M, which is the order, we have to use the ceiling function, which means that if we have a real number, if we divide 5 by 2, for instance, we're going to have 2.5. So we have to approximate it to 3. That means the node that we contain within the internal node should be between 3 and 5. We will see examples to illustrate this in future slides. So comparing the 2-3 tree and the B tree, based on the nodes, for 2-3 tree, it contains 2 nodes or 3 nodes. Recall that the 2 node is talking about a node that has 1 data item, and 3 node is referring to a node that has 2 data items. But for B tree, it's a bit different because the nodes range from M divided by 2 to M. And remember that M is the number of the order of the B tree. So if we look at number of data items under 2-3 tree, the number of data items could be calculated using 2 to power h minus 1 and 3 to power h minus 1. But for the B tree, we can do the calculation using 2 divided by 2, m divided by 2 to the power of h minus 1 and m to the power of h minus 1. Apart from these two properties, the constraint property is similar because in both of them, all leaves or all the leaf nodes must be on the same level. So that's one similarity between the 2-3 tree and the B tree. Okay. Now, if we ask this question by saying, or if we say that a 2-3 tree is a B tree of order 3, do you really agree? Do you agree on that? Yes, you can think about that and relate to the structure. If you look at the structure, how they are structured, and the kind of the order of these two samples of 2-3 and B3, you will realize that the 2-3 is a B3 of order 3. You might have a contrary view, but you can discuss that when we meet at the tutorial section. An assessing node in a B tree. We want to see how we can assess node in a B tree. One thing that we also need to remember is that each node in a B tree is known as a block or a page of a storage, secondary storage. And we know that accessing node means having access to the secondary storage. And you, from computer science experience, we might have understood that it is quite expensive to access memory that are outside the main memory, like the secondary storage memory. So in that case, the fewer the number of nodes we have, which is also known as the block, the better for us because it reduces the computational complexity of the operations that we're going to perform. So yeah, this is more explanation of what we have said here. Okay, now let's have put these things that we have said earlier in a structural diagram. So in this case, we have a B tree of the order of 5. So now this first thing that comes to my mind, which I think is also helpful, is that when I see the order, I'll tell myself that none of the nodes will have more than 4 data items on it. So if it goes up to 5 data items, then that node need to be split. We'll see examples about this, how we can split the node. So if you look at this B tree, we see the maximum number of data items we have in each of the nodes is 4. So now it says here that the root node has either no children or 2 and m children. So in this case, the root node has only 2 children, but the root node can have 3 children it can have 4 children because this is the order is up to 5. Then the internal node must be between 2 divided by 3 by m by 2, which is equal to 3, and m. So this implies that each of these nodes here, the internal nodes, they will not have less than 2 nodes. They will have from less than 2 data items. They will have either 2 data items, 3 data items, or 4 data items. And lastly, all leaves are on the same level. So we see these are leaves and they are all on the same level. So if any of the leaf is somewhere here, then or somewhere at this point, which is not on the same level with this, then this tree violates the B tree properties and it cannot be called a B tree anymore. So a few other observations that a full and balanced binary search tree is similar to a B tree of order 2, but managed differently. So for a full and balanced B tree, it is very similar to the B. For a full and balanced binary search tree, rather, is very similar to the B tree, but the order on how they are managed varies. So also recall that in this case, the balanced tree, the binary search tree has 2 nodes. Two children nodes. So in this case, now when we have 2 order binary tree, you realize that you're going to have also 2 children node. And again, we have that a 2-3 tree is a B tree of order 3. Okay, so though we didn't cover this here, but you can also remember that a 2-3 tree has maximum of 2 data items in each of the nodes. And this is applicable to the B tree of the order of 3. Likewise, the 2-4-3 is also similar to a B tree of order 4, but they are managed differently as well. So if these are the conditions, so what is the difference between a general binary search tree and a B tree of order 2? The one thing is that a general binary search tree does not have all its leaf nodes on the same level. So that is one difference that you can use to explain why the general binary search tree is not the same as the B tree of the order of 2. Now, let's now look at further observations on the B tree of the order of 5. So in this case, we have explained this earlier anyway, but I think in this place it is a bit clearer. So what this is saying is that in each of these nodes, it must have m is 5 divided by 2, which is sealed to 3, and the number of uh, children will be maximum of 5. So this also implies that we can only store between 2 and 4 data items in each of the nodes. So this node has 2, this node has 2, this node has 2, and this node has 4. So except the root node that can contain only one data item. The observation again, we have these for a 6 for order 6. So in the case of order 6, which is similar to the order 5, we divide 6 by 2 to get 3 and the 6 children. So in that case, we can have two data items in a node and maximum of 5 data items in a node. Okay, so in this case, we have looked at the minimum height of a B tree. And what about the maximum height of a B tree? I'll refer you to an activity we've done previously as activity 16.1, where we use this to find that the number of data items in a 2-3 tree of height h is between 2 is to power h minus 1 and 3 is to power h minus 1. And the height itself is a log n of plus 1 and log 3 of n plus 1. So in this case, if we want to store 1,000 items in a 2-3 tree, then the minimum height and the maximum height, this could be under 3 nodes, which is saying that we need to store 2 data items per node, or it could be under 2 nodes, which is also saying that we need to store 1 data item per node. So in that case, if we can have 7 height and 10 height in these two conditions. So this is equivalent to the binary search tree, but all the major difference is that all the leaves are on the same level. So in this also implies that the if we are to search for the 2-3 tree, with the data stored externally may be the worst case scenario where we have to access 10 disks outside the main memory. Now, is it possible that only 2 nodes are used? What about only 3 nodes? What is the possibility? What is it possible? When is it possible? Sorry. Is there a constraint on the number of nodes? Yeah, I will put it this way that you will also need to remember that in binary search tree, the number of nodes are not at the same level. So, but for a B tree, the number of nodes must be on the same level. So there's a constraint on the B tree. So if we further discuss this, then we can ask that if a B tree has order of 128, then the maximum of that per node will be 127. And this per node is referring to the first height. So if you want to calculate for the second height, then it will be the first height, which is level 0, plus that of the level 1. So for a height of 2, remember when we have a height of 2, we label it level 0, level 1. So it will be level 0 plus level 1. And remember, level 0 is 127, then level 1, which is the second level, is 128. So the multiple of this is going to give us maximum of 16,382 data items stored. So that means we can store 1,000 16,383 data items. And these 16,318 data items are stored on two levels. So it implies that we can access the external disk for two levels, or we can access the external disk in two different ways, which we can access it. If we use the 3 nodes, then we can have a height of 9. And if we consist of 2 nodes, we can get a height of 14. It is a question, say, can we have 3 trees of 2 nodes only to contain any number of items? We also recall that the definition and the constraint of the leaf node. So the constraint of the leaf node plays a major role here. Then let's start performing some operations under B tree. The first operation we're going to perform is searching operation. So for searching operation, we start at the root node and perform the binary search on the key that we want to search for. The first condition is if the data item is found at the root, then our search is complete. But if the data item is not found at the root, then we have to continue our search. And if the data item we get to follow our search for one particular direction, and we get to the root and we can't find the leaf node, and we can't find the data item, then we term our search to be unsuccessful. Otherwise, we keep going to the second root or the second part until which we can call the branches, until we get to the point where we can find the item that we are searching. So I say questions that says, what is the efficiency in terms of the big O notation of searching in a B tree? Yeah, in searching in a B tree, we have seen that a B tree is maintains sorted data, and because it maintains sorted data, then the search is it's not going to be the kind of search that we have to go through all the nodes to find our search. So the case scenario here is that the worst case scenario here is when we have to look at any side of interest to get to the search position where the data item is found. Then in using that kind of search is going to be if a cost of a big O notation of the order of log n. Then another operation is insertion operation. For insertion operation in B tree, it is similar to the 2-3-3 insertion operation. So in that case, the tree is searched to locate where the item, where to insert the new data item. Then there's a condition that is if node is not found, is full. So if that node where the data item need to be inserted is full, then is not full, pardon, then we insert the item and we complete our operation there. But if in a case where the node is full, that is, the node has the maximum number of data items that it needs to contain, then we need to perform further operations. And the further operations that we can perform is First we have to split the node into two and move the middle key or the middle data item to the root node. I call it promoting it into the parent node. So if the parent is also full, then the same operation will be performed where we have to split the parent data, the parent node, and promote the middle item to the then parent node. This operation will continue until we find an empty space where the data item that we are promoting can be inserted, or we will create a new root node for the data item to be inserted there. So what is the efficiency of the insertion in binary in B-tree? Of course, the efficiency in inserting in B-tree is also of the big order. Sorry, it's also of the big O notation of the order of log n. This is because this insertion follows the order of sorted data, where we don't need to go through all the nodes to find the location where we need to insert the data. Okay, now let's have a look at one example to explain how we can insert data into a B-tree. In this case, the B-tree is of order 5. So it's of order 5. That means that each node can contain maximum of 4 data items. So if that is the case, then we can have these 4 data items at first move. So in that case, we have CNO U as our first data item. Then the next data item we are going to add is P. So if we add P, we can add P here. Then when we add P here, we can see that we have violated the properties of a B tree. And to still retain the property of a B tree, we will need to split this node into two and promote the middle. We have to promote the middle data item after inserting P, then split the remaining one into two. So when we insert P somewhere here as OP, then U. So that means we're going to have another space like this where U will come in here and P will take this position. So this is the middle one, which we're going to promote to the root node, and we will split this to get CN and the PU. So yeah, now we have inserted P. We can insert other data items. At this point, we have only two. We have only two here as well. So we can pick YRIG, insert I and G here, and insert Y and R here. So the next data item we need to insert is H. So where do we insert H? We can insert H at this level, at this node. But when we insert H at this node, we will exceed the maximum number of data items that this node can contain. Then we have to, because of that, we have to promote the middle data item, which is going to be H in this case, to the parent node, and split this node into two. So if we do that, we split this node into two, we're going to have CG in, then promote H to this part. So this is what we're going to continue doing. We'll do the same thing for T, promote T. We do the same thing for ABL. So when we add ABL, we're not going to promote because none of them exceeded the maximum data items they should contain. Then we insert another data item, which is E. When we insert E here, we're going to promote. We promote it to this level, promote C to this level, and split the node. Then we're going to insert S and K. We insert S and K. So we've inserted S and K, no promotion. Then the next one we're going to insert is J. So when we insert J, do you think we're going to promote or we're not going to promote? Think about this. So where can we insert J? Can say IJ. So we're going to insert J here. This implies that we're going to promote. And when we promote, what is going to happen? We will promote K and split this. But when we promote K, we realize that at this point, the node is full. So K is not going to fit in here. So we're going to split this again and promote K up. So if we do that, we have K, we have this node splitted into two, giving us CH and OT, CH and OT. Then we have all the data items attached to them, or the children nodes attached to them. So at this point, we have completed the insertion operation, and this also maintains the properties of a B3. Another operation we're going to perform is deletion. We're going to delete data items from a B tree. So now we've been given a list of data. That from the list of data we form a B tree. That's create a B tree. And after creating a B tree, we're going to delete these data items from that B tree. So first, we have to create the B tree from the data item, following the steps we took in the previous slides. So we use the data items to create this B tree. When we finish creating the B tree, we now have to look at how we're going to perform the deletion or the delete. We're going to delete these data items from the B tree. And yes, to perform this deletion operation, there are certain things we need to consider. The first thing we need to consider is to find out if the data we need to delete is not a leaf node or data item in a leaf node. So if that data is not in the leaf node, then when we perform the deletion, we will have to replace that data location using either the process predecessor or the successor. To determine which of them we're going to use, we will see that when we perform the operation, the example, from the example. Then this implies that we also need to check that there is enough data or enough item in the leaf node. If the data is in the leaf node, we should try and check that there is enough data item in the leaf node. So now, if we check and realize that the leaf node where we want to delete the data has maximum or enough minimum number of data items, then we can delete the data and we do not need to perform any operation. But if that leaf node has just the minimum number, is not more than the minimum number, let me go through this again. So, I mean, if the data item we want to delete is in the a leave node, and that leave node has more than the minimum number of items that it's supposed to contain, then we can delete that particular item in that leave node, and our operation will complete, we stop there. But if the item that we want to delete is in the leave node, and that leave node only has the minimum number of data items, then we need to perform other operations after deleting the data. So we cannot delete the data directly. So we need to check the adjacent leave node, and if possible, move the adjacent leave node to replace the data that we have deleted. And another condition is that if there is no space or no spare data in the adjacent node, that is, we don't have any spare data in the adjacent node that we can use to replace it, then we have to move to the predecessor and combine the nodes. We will use an example to illustrate what we have just said here. Now, let's look at this example where we have given a list of data items that we have to create a B tree and delete data items 8, 18, 15, and 4 from the B tree. Already we've created the B tree in the previous slides. So let's bring it forward. So this is the B tree we created using the data items that we were given. And the thing we want to do is to delete the data item 8. So the first move is to find where data item 8 is located. So in that case, 8 is less than 10, so we move left. 8 is greater than 6, so we move right. And this is 8. So those things we explained earlier is that this is a leave node, and the data item we want to delete is in a leave node. But that leave node contains more than the minimum data items that are required to be in a node, because the minimum is 2, but it has 3 data items here. So in this case, we can delete and our operation will be complete or completed. But so in that, let me stop there. We'll explain the rest later. So in that case, if we delete 8, we're going to delete 8 and we'll have 7, 9 left. Then the next data we have to delete, the data item we have to delete is 18. So where is position of 18? So the position of 18 is here. And now when we delete 18, we realize that the data item left here is just 1, which violates the property of B tree, because the property says the minimum data item is 2. So we have to do something. What we can do is that we can borrow a data item from the adjacent node. On the adjacent node here, we can borrow from this node here because all the data items here are greater than this. And if we borrow here, we're going to have 1 data item left, which violates the rule as well. So if we borrow 19 from this place, put it here, then we have 20, 21, and 24. And that will restore these 3 to B3 properties. So if we move forward, we're going to have 19 coming up to this place, 20, 21 at this place. Then the next data item is 15. So where is 15? This is the location of 15. Then this 15 is located at the leave node. But if we delete 15, we're going to have only 1 data item. which means that we need a data item to replace the position of 15. So where can we borrow? We can borrow a data item from here. But if we borrow a data item from here to replace here, here it becomes 19, and here has a hole. So we need to fill this hole to make this tree or this node, to restore this node to binary search tree, to B3 properties. So what do we need to do? We can go to the adjacent node, which is this place. So at this point, this node has more than the minimum data items. So we can take 20 and place here. So in doing that, we have 19 coming down, 20 going up. So we're going to have final value, which is 19 here and 20 here. So the last one, I suppose, is 4. So we want to delete 4. So on locating 4, we have 4 here. When we delete 4, we're going to have a hole here. And if we have a hole here, we can borrow from this place to make up this hole. But when we borrow from this place, we're going to have a data item, leaving a hole here. So we can borrow from the neighboring successor node to make it 10 at this point. But if we make it 10 at this point, then we're going to have a situation where this violates the the B3 properties. So it is at this point that we need to combine the nodes to restore this tree to the B3 properties. So first we delete 4 and we replace with the data from here. So we have 5, 6. So we replace with 10 here and combine this one. So if we do that, this is what we're going to happen. So what's going to happen is that we have 6 here. We have 1, 2, 3, 5, then 6, 10, 13, 20 arranged in this way. So if you go back, we have 20, 20, we have 13, we have 10, then the 6, because 3 will come down to replace this 4. So finally we have 6, 10, 13, 20, and the leave nodes are 1, 2, 3, 5, 7, 9, 11, 12, 14, 19, 21, and 24. So yeah, this is where we're going to end this part of the lecture. As usual, you have some exercises on B3 that you would want to try your hands on. And there's a question here which says, what happens if we require all the keys in a B3 to be printed out in ascending order? So one way to answer the question is to use use in order traversal requirement or in order traversal operation, or use the B3, which we're going to discuss in the next lecture. Thank you so much and have a nice day. Bye.